Hello, hello.
It's on now. Just checking I have a rapporteur. Oh. Okay, welcome to the From Observations to Products, Advances in SST Calibration, Validation and Product Assessments. I should say at the start that we have one talk that's been withdrawn, unfortunately, which is a great shame because Chris Merchant and I were only saying yesterday how much we were looking forward to it. But so we have maybe a little bit more relaxed time. We could either decide to take questions after each one, which may be not a bad idea, or we can maybe even try and get a full coffee break in. Okay, something like that. Okay, so without further ado, I hope we have Christo Whittle, who's going to give a nice 30-minute.
Yeah, no.
And he knows he has 30 minutes plus now, so, you know, make yourselves comfortable. 20 years of upwelling variability in the southern Benguela, an intercomparison of Benguela optimized MODIS SST to a MUIR 4.1, OSTIA version 2.0, and CCI version 2.0. There's some catchy titles you come up with. Okay.
All right. Good morning, everyone. The title is longer than the talk. So I'll get right to it. The reason for looking at data, those four products in that way was I'm investigating harmful algal blooms in the southern Benguela. And there's a general consensus, there's an increase of harmful algal blooms in the areas affected by them in conjunction with an increase of marine heat waves or warming events around the world. And so the hypothesis is that if we are having an increase in ebb currents, we expect an increase in warming events. And we should find the right tools to detect it early and then also be able to detect the harmful algal blooms and perhaps also then predict not only the occurrence, but also the translation of these blooms eventually. So using Earth observation tools, I want to kind of find the ideal physical drivers that I can obtain from satellite data and then track these blooms. So large red tides occur in St. Helena Bay, and St. Helena Bay is marked SHB. It's the big red circle. This is the southwestern part of South Africa. You can see the southern part of South Africa. And to the south, just south of Cape Town, you have Walker Bay. And these two areas are prone to harmful algal blooms. The phytoplankton blooms are quite large in St. Helena Bay, can extend up to 50 or 60 kilometers, and are dominated by dinoflagellates, essentially. The southern Benguela is essentially kind of a case 1 water type, extreme case 1, lots of CDOM in the water, but all the variability, most of the variability related to phytoplankton or CDOM, and not so much to sediment and so on. When you have these large blooms, we have oxygen depletion in the water column, and besides the toxins that collect in the tissues of the mollusks, this oxygen depletion also affects the other living organisms. Sometimes it's killing, if it's large enough, fish kills, but also as it approaches the coast, we have an effect on the lobsters who then get trapped between the surf zone and low oxygen water and sometimes wash out, causing big economic loss. I'll show an example of that. And then, of course, there's also mechanical damage to the gills of young fish, and then that affects the spawner biomass and the recruitment in the following year. So predicting the extent of these events are quite important economically. So this is an occurrence in 2022. Usually the harmful algal blooms occur in the early part of the year for us in summer. So summer, early autumn, and this is a picture of some lobsters that have actually been stranded on the beaches near Lambert's Bay and Elands Bay in the St. Helena Bay area. And it's a response standard operating procedure to decide what to do with these lobsters once they're stranded. Try to harvest them, try to get them back into the surf zone beyond where the bloom has occurred, or to put them in temporary storage tanks. So if you have early enough warning, you can get the mechanics in place to have the right equipment to respond to this kind of event. The other effect that it has is also with aquaculture. So we have in Walker Bay, aquaculture farms several. It's also spreading to the west coast, to the Lamberts Bay and Durham Bay area, in St. Helena Bay as well now, for farming abalone. And abalone is a high value resource. And you can make, and it can generate quite a bit of income for smaller communities because of the farms, can employ people who are then not able to access or have enough seagoing days all the time to access artisanal fishery. So, what makes this bay so special? St. Helena Bay is a concentration area because of the way of the shape of the bay, the way it's set up, and the prevailing winds. We have a concentration area towards the south of the bay, where over a long period of time, if we look at the 5-year mean from Seahwoods over there, there's a high concentration of chlorophyll essentially in the bay. And the way it's set up for the occurrence of harmful algal blooms, it's an initiation of an active phase of southeasterly winds blowing along the coast, causing upwelling plumes directly from Cape Columbine that you see towards the south there, a large plume usually, and it traps upwelling waters from the coast between this big plume, and it causes this front, which is quite nutrient rich. So you've got the production that follows that. But of course, there's a succession of phytoplankton because during this event, in the active phase, the water column is quite unstable and turbulent. And during the relaxation phase, when the winds actually dissipate a little and it's quiescent, we have a predominant proliferation of dinoflagellates, which results in these blooms. Also during this quiescent phase, these waters move toward the coast and towards the south, and this is when we have the impact on the coastline. So predicting these conditions is what I'm after. This one is just showing how the bloom might migrate south towards in a relaxation phase. But what drives these is the combination of the position and the translation of the South Atlantic high pressure system during summer, austral summer that is. And this high pressure system modulates the upwelling and then modulates the upwelling events and also the quiescent events, and how frequently we would have long enough periods of stability in the water column to promote the occurrence of harmful algal blooms. So from a physical perspective, I want to be able to look at the winds and then also look at the response to these winds, look at the upwelling plumes themselves, identify that, and see whether the data that I have will identify consistently at the right periods. And then look at the response in terms of the chlorophyll A concentration. So in terms of data, I've been using the CCMP data set, which is a blended wind product from satellite data, 25 kilometer, but it's resolves the St. Helena Bay, okay, and the upwelling over there, and also the Capes quite easily. And then also look at the multi-scale ultra-high resolution, the JPL product here. And I think this is the most recent version, 4.1. And then the most recent OSTIA version, and then also CCI. And the reason to compare that is, well, even though I can use MODIS to blend and create a daily product, I still end up with some cloud days. And we want to compare to see how well the level 4 products respond to the variability in the region. And then calculate the Ekman upwelling from the CCMP, just the component along the coast, depending on the orientation. And then calculate some, use the Hobday method to calculate some marine heat wave indices, or at least calculate the presence of marine heat waves within the bay and see how those the frequency of these waves are actually intersecting with the occurrence of harmful algal blooms. All right, so initially, the MODIS product needed to be validated, and I think many of you guys have seen this before, but essentially it was a matter of using the variability inherent in the MODIS. So getting the standard deviation per pixel and using that excuse me, I think my watch just answered somebody. Just sorry. And so using the inherent variability in the MODIS product, using the standard deviation per pixel, and then using that variability together with a 5-day moving average. And also recently, I've been including OSTIA in that analysis to help me to decloud the data, at least identify the cloud, and then combine all 4 overpasses from MODIS per day to create generally a daily average. And I'll show the results of that, but essentially the sequence of images shows what A with no flags, B with using the strictest science flags, what we would expect in nighttime data only. And then C is like toning it down a bit, only using the albedo reflectance flags and first identifying the cloud and then using that cloud identification method to identify some of the cloud ringing and then doing that for all the different overpasses on a day and then combining that to create the daily product in E. F shows just how well the gradients are retained when this is done, so I can still actually maintain the variability spatially. The graph right next to it is just is a time series of a thermistor in the upwelling cell just off the Cape Peninsula, and I'm recording the variability. So it's at 5 meters depth. So I'm not looking at the sea surface temperature itself, but just at the variability and how well the data captures the event scale, captures the upwelling events. So you can see that the bottom two graphs are kind of well correlated. The difference between them is due to the depth difference at which the two temperatures are taken. Top one is a multi-scale ultra-resolution product, and that one has got a strong warm bias, and it's actually not capturing that upwelling event scale at all. So after doing a Fourier transform and collating the in situ data with the Earth observation data, I get a very good correlation. So I'm quite happy that this product is actually resolving the event scale at the periods that I wanted to. The added advantage, of course, is then moving from one, just using Terra or Aqua. This is a pixel retrieval, valid pixel retrieval over January for the whole data set over 20 years on average. And you get about 50% retrieval in my region of interest on the west coast between Cape Point and into St. Helena Bay. And lower retrieval for Terra because it's in the morning, there's a bit more cloud. And then higher retrievals for Aqua. When you combine the two, get very good retrievals. Of course, and that's in the third image showing you very up to 80% in my area of interest. Of course, this varies throughout the year. At the bottom, I have seasonal averages of these retrievals to show this variability and also then give me the provides the motivation for looking at the level 4 because, of course, there are still gaps and want to make sure that those monthly averages that I'm using for looking at trends are representative. So over here, at the time, I was just looking at some other reanalysis data and then also model data just to compare to the product. The Western Agulhas Bank is pretty much its own province. It's unaffected by the Agulhas current and its presence, and it's got no upwelling that influence it. So the Western Agulhas Bank is almost like looking at the Southeast Atlantic. In fact, it's way calmer because there's no passage of Agulhas rings. So all you see is a seasonal signal, and in this regard, the MODIS product agrees very well with the other three products I was looking at. But as soon as you move into the upwelling zone on the southern Benguela shelf, you start seeing separation between the products. And especially in the summer, during the upwelling season, you start seeing separation, especially with Glorious and Highcom. But Brand still seems to have a very close connection with what's happening with MODIS. Moving then into the upwelling zones, the active places I was looking at, Overberg is the area where Walker Bay is, where the abalone farms are. So Overberg is also showing some strong separation, and now even Brand is showing that. And in the Cape Peninsula, even stronger within the upwelling cell. So then looking at the climatology of the three data sets I was looking at, the MODIS data has got two strong cores at Cape Columbine and at the Cape Peninsula. It's absent in the MUIR data set, but OSTIA does capture it at the Cape Peninsula, although it's moved a bit further north. And the CCI also captures it, but it almost connects that whole upwelling zone into one big zone. So it doesn't differentiate spatially between those two core upwelling cells well enough. Then looking at the variability, look at the standard deviation. Of course, we expect high variability at both those two locations because of the translation of the intermittent translation of that high pressure cell as it reaches around the coast. So high variability, a strong pulsing of the upwelling cells over there. It's captured in OSTIA and to CCI and CCI to some extent. MUIR, not really. And then when we look at the biases, oh, there's a massive warm bias from MUIR. a little bit in OSTIA and CCI, but what was surprising for me was the cool bias that I'm observing. It's about between 0.5 degree to 1 degree within St. Helena Bay, sometimes more than that for the CCI. And this is again the January to March, basically the summer seasonal mean for the bias. And then looking at the cost function to see how these differences between the products actually relate to the standard deviation within the MODIS dataset. Well, in MIR, it's a problem. It doesn't resolve anything along between Columbine and the peninsula, and also further south up to the southernmost point, Cape Agulhas. But CCI and OSTIA, it's within one standard deviation. It's kind of like acceptable within the variability of the data set. So we should still be able to resolve the variability. Looking then at seasonal signals for these three products at those locations and separating it again into the Agulhas bank, you can clearly see a nice seasonal signals, solar warming in the summer, winter mixing, and then rising up again from October to December. And the four data sets are indistinguishable in this area. Again, when we move to the West Coast, we start seeing the separation during summer of the data sets, with MIR being the warmest, and then OSTIA, CCI, and MODIS being quite close to each other. As we look at the Cape Peninsula, and then I've added Port Alfred. I didn't actually point it out, but Port Alfred is a upwelling cell on the southeastern part of the coastline, and that's driven by both the Agulhas Current and then also some wind-driven upwelling as the high pressure system reaches around. And and also at that point, we see some separation where again the upwelling is not being resolved adequately, but at least the other three products seem to agree much better. This is the monthly bias. It just reaffirms what I've been saying and also showing spatially earlier, but this is at the locations, how pointing out that at the most intense upwelling locations, there's the biggest difference between MIR and the rest of them. And within St. Helena Bay, it's less of an issue, although in St. Helena Bay, there is a cool bias both from CCI and also from OSTIA. So, and this is the cost function. I'm sorry, this mislabeled this, but it shows again, no, this is not. I went the wrong way with the arrows. This is the cost function. Okay, so again, showing that the variability is actually okay for the most part, Agulhas Bank, West Coast, and even in St. Helena Bay. But for the upwelling cells, it's a problem with MIR. So then looking at some long-term trends, and well, from the MODIS data set, which is this MRSU that I've put up here, and MIR, you can see the red is MIR, the blue is the MRSU. Actually, there's a lot of variability interannually, but there's no clear trend for the MODIS data. And this is within St. Helena Bay. Okay, so lots of interannual variability, but no clear trend in terms of, yes, there's an increase in upwelling, or there is an increase in temperature within the bay. Slight negative slope with the MUR, but there's also a bias there associated with it. The CCI is quite close and has a very strong correlation, whereas the correlation with the MUR is quite weak, even in St. Helena Bay. This is again looking at the Cape Peninsula, so now we're looking within an upwelling cell, and then the bias is just huge, 1.4, and this is the average bias for the time series, the differences between the two curves. And the variability in the MIR data is quite big, but that's an interannual variability and no short-term variability is captured. In the anomalies, again, correlation is not as strong, whereas in the CCI, the correlation is quite strong, and the data sets over the whole time series are quite close. So looking at the event scale, and so we were talking at the start of the talk, I was talking about an event where there was a lobster walkout in early March in 2022. So the green bars are chlorophyll constant areas of high biomass greater than 25 milligrams per cubic meter. And that's the areas per square meter. And the bars represent like large areas of harmful algal blooms. And there's a big warming event at the start picked up on the OSTIA marine heat wave index and followed immediately by some massive harmful algal blooms. And then a bit later in the month, when the upwelling picks up just a little, some more harmful algal blooms. And when you look at the wind at the bottom, and this is just the Ekman volume transport, the blue represents active upwelling, the red downwelling, the green is the wind strength. Okay, so with the winds being quite low, we had a warming event at the start of the season, and then with the pulsed upwelling feeding this bloom, it just grew and became quite massive within St. Helena Bay. But now, just because there's a big bloom in the bay doesn't mean it's actually affecting things close to the coast. So identifying the conditions for a bloom event is quite possible. Then you can even do some kind of machine learning probability for it using the wind, the SST, and then the resultant expectant chlorophyll bloom. But the translation of the bloom is an issue in terms of determining how it's going to end up at the coast. This is the same year. Now, just looking at the MODIS data, I'm sorry that I didn't put the green bars for the, but it's the same graph you'll see. So on top again, that's harmful algal bloom, and at the bottom, these are the warming days recovered from the MODIS data. And you can see that although OSTIA seems to be quite structured, two big events, one small one, there's intermittent warming days being detected by the MODIS algorithm. And the way I did the marine heat wave index is I only have a 20-year period because that's the period of the MODIS data set. So I kept it consistent for MODIS, CCI, and also OSTIA. So 20-year averages for all of them, and then using the method of Hobday to calculate the index, both relative to those data sets only. So they show some different results. And overall, high biomass, there's not really an increase or a trend very clear in terms of the biomass within the bay, but there's big interannual swings, which could be related to some either climate modes and perhaps the position or intensity of the South Atlantic high pressure system and how it's driving the upwelling. There's an increase happening in Walker Bay, though. That's the graph at the bottom, the orange, and and that shows that there's a slight increase in terms of harmful algal bloom occurrence over the last decade or so. But then looking at the cumulative upwelling within St. Helena Bay, this has decreased over the last 2 decades, whereas within Walker Bay, there's been an increase of the upwelling, and this seems to be going with what's happening also with the increased phytoplankton blooms. Then looking at the warming event days, it is actually just having the opposite slope to what's happening with the cumulative upwelling. So different indices, the one is just coming from the sea surface temperature, showing warming events, and the other one is the upwelling calculated from the wind. And with the upwelling increasing, there's a decrease in the warming and vice versa. So it's kind of confirming that at least those two physical parameters will be able to predict the precursor conditions quite accurately. Unfortunately, I ended up with this. And this is very confusing spaghetti, right? But it's the 4 products. And that's the amount of warm event days from January to April over the course of this data set. And yeah, there's big interannual swings between the amount of warming event days, but also the trend lines are quite different. So for St. Helena Bay, we were looking at no particular trend at all, I think, or a slight decrease. And for Mir, there's like a strong decrease of warming events, and there's some convergence with CCI and OSTIA. But yeah, so which one to trust, even though the same method was used inherent and using the data, the climatologies within those data sets, I'm getting slightly different results. The natures of the curves are similar, at least for OSTIA and CCI. It's just the amplitude of the events that differ, but at least the swings, interannual swings, are consistent. It's also there in the MODIS dataset, but there seems to be some kind of adjustment in terms of how many events are being recorded. So, high biomass blooms are frequent. Associated with phytoplankton biomasses, do you have some impact on the living marine resources? I was able to demonstrate yes, so we can use the Earth observation data to at least predict the precursor conditions. We can see the events emerging after you've got warming events, after you've had upwelling events from looking just at the wind index. Having SST and chlorophyll coincident works quite well in terms of saying we're confident that this data is representative for both chlorophyll A and SST. I haven't talked about the chlorophyll A algorithm, but we just don't have enough time. The SST clouding works quite well. I'm getting very high retrievals during summer, but even during the rest of the year, up to 60%. So I feel comfortable it's representative in terms of what the month is showing me for what's the average during the period. Yeah, that's the improved spatial. The Ekman transport correlated well with the SST index in showing when the warming events are, also the cooling events. And the expected inverse relationship between the upwelling and the warming events was shown between the SST index and also the Ekman upwelling. There was divergent warming event detections from MIR and then from the level 4 products. The large internal swings were seen in the cumulative upwelling, and the chlorophyll, as I mentioned earlier, although we have large blooms, being able to predict their impact is not so straightforward just using these methods. So a combination of having a probability of bloom occurrence and then also being able to show the translation using a drift model and some hydrodynamics would actually help to be able to predict maybe within a couple of days advance for people concerned with these issues of the impact that the blooms may have. Yeah, and I think also investigate the connection to the translation and position and intensity of the South Atlantic high in relation to the upwelling to see what's happening with these interannual and climate modes that might be inherent in the data. Thank you.
Very good. And I thought about reaching for the 5-minute one, but then you hit the last slide. Oh, never mind. I'll just leave it. Do we have, I think we'll take questions now. We've got a lot of time. David?
A part of what may be going on with MUR is the hierarchical approach they use during conditions of clouds. They use only nighttime data. If they don't get a MODIS pixel within plus or minus 2 days, then they switch to nighttime ABHRR within the plus or minus 2 days, but it's only nighttime again. And if they don't get either one of those data sets, then they switch to AMSR. And so now you're using a huge pixel that's going to pick up stuff outside the upwelling zone, perhaps, and that could account for some of your funny biases that are occurring.
It's also, I agree. It's also there's the positioning of the escapes within the grid cells, the grid positions. So when you have those 25-kilometer big pixels, it actually completely masks the upwelling because of the location of the pixel relative to the core of the upwelling cell. So that plays well. You're right, definitely. I think so as well.
Anybody else got questions?
Yeah, this is Jorge. I'm sorry, I'm online.
Go on, Jorge.
Oh, thank you. This is Jorge from NASA JPL. Kind of following on to David's comment. I wanted to ask you, forgive my ignorance, Christo, when you did the cloud masking in MODIS, did you use the quality flag 0 to 5, or did you do your own cloud masking? And one of the reasons I'm asking, yeah, there's a poster with David Weezy and Yetziani that we actually did some similar comparisons with gradients off the California coast and issues with upwelling, and we also saw differences, especially with OSTIA. And of course, one of the issues that we think that caused those differences was the cloud masking, and also the fact that OSTIA incorporates, for example, geostationary data, which would improve the cloud issues, especially off of California, which can be pretty dominant in certain months. So anyway, I just wanted to ask you quickly, thank you for that great talk, and ask you quickly if maybe some details on how did you apply your own cloud masking to the MODIS data?
So for the daytime data, I actually tried only to use the albedo mask. And then the nighttime data, I would be quite strict and use the quality flags to retain, as far as possible, the highest quality scientific data. I then use the data within a 5-day composite and running kind of mean. And as the data is being cleaned up, they would be included in the mean. And then I would compare the central date to the mean and within a 1.5 standard deviation. So anything outside 1.5 standard deviation, any difference would then be excluded as cloud. I found that including OSTIA on the day that I'm analyzing actually improved the process slightly, and I've been using that to help augment the cloud with the declouding.
Okay, thank you. Yeah, that because I feel like that's a major issue in these coastal applications right now. Thank you.
Yeah, I actually had. Does anyone else? Oh, go ahead.
Christo, yeah, I was going to ask you a question along the lines of Jorge's question. How confident are you that these differences that you see between the optimized MODIS products and the other level 4 is not coming from potentially high gradients during upwelling events being misclassified or flagged as clouds?
Sorry, I couldn't hear you so clearly. There's kind of an echo. Could you repeat the question, Marwan?
Yeah, how confident are you that possibly during upwelling events you have high gradients?
Mm-hmm.
These high gradients are being flagged as clouds.
Oh, okay. So I cannot give you like my level of confidence other than my observations. I haven't quantified it statistically, put it that way. But the persistence of the gradients in the product after the declouding has been quite positive. I've been able to follow gradients where I know there are fronts associated with features and not be picking up those gradients on the edges of clouds. Does that help?
So the masking, the clouds masking is not based on gradients. It's mostly based on statistics.
It's mostly based on statistics. I try to avoid using the gradients for masks because I want to retain the gradients for the feature recognition.
Does
Thanks.
anyone else have a question?
Sorry.
Oh, okay.
Just Marwan, of course, in the nighttime quality flagging, some of the gradients do get picked up on that. But then when I do the compositing with the daytime data, it usually takes care of that.
Yes, thank you. Stock. I see you have used quite different data sets.
Mm-hmm.
In your opinion, which data is the best for your case studies?
So I think the level 3 MODIS dataset is really quite good in terms of feature recognition and also tracing fronts and so on. Of course, it's also a higher resolution, 1 kilometer, but the level 4 products, the most recent ones, both CCI and OSTIA, seem to resolve the variability quite well. The biases that I'm picking up are very, very close in shore in the core of the upwelling cells, and it's probably related to resolution of the 2 different products, right? Because I'm subsampling or oversampling to compare to MODIS. And I don't know, I still want to discuss a bit with Owen and Chris around the cooling that I see in St. Helena Bay, that was quite unexpected. I expected the warm bias at the upwelling cells, the small section next to the coast, but the cooling was a bit, the cool bias was a bit surprising. So I'm not sure why.
Have you ever to like a bias correction using like institute data and also perhaps using also this sea and land surface temperature radiometer is the high resolution data to improve your data sets?
So with the land influence, I actually mask out a kilometer or two in the MODIS data set from the land to kind of try and avoid that contamination. I do think sometimes diurnal warning could be an issue, but I try and use the flag to exclude low wind conditions. So yeah, I'm at a loss for why those two products are actually different in that, and it's consistent with OSTIA and with CCI, but to a slightly different degree.
Chris has got a question or comment or response.
Thank you, Chris Merchant from Reading. It's a very interesting talk. Thank you, Christo. And I mean, I was surprised that any of the level 4 products really were capturing some of the features because they're not at all optimized for these coastal zones. Quite often, they will not be taking any real SSTs that close to the coast, and they sort of get extrapolated to the coastline. So that's it's encouraging that there is some usefulness of those level 4s already. But I was wondering, obviously with the high resolution missions coming, as well as the importance of the coastal zones, could GRIST be thinking about analyses that are more specifically targeting just the coastal zones rather than the open oceans? Because it's a different problem, and we might use different solutions to address, to optimize those two different situations. I mean, would you as a user welcome that, and what sort of properties would you like such an analysis to have?
So thank you for that question. I think that's a great question, and we are leaning towards looking at that higher resolution in very specific areas. Some areas are just prone to having very strong dynamic conditions where you have the setup of fronts that are precursors to other events, harmful algal blooms and such. And the resolution, even at the 1 kilometer, is not actually going to pick up exactly what you want when it comes to predicting this kind of event. And yes, it's useful, at least at picking up the heating, but the translation of these fronts is being able to look at the rate of that translation will give an idea of how fast a bloom is moving somewhere, and you can compare that to hydrodynamics to say, do that kind of tracking. So in areas where you have these kind of high biomass blooms, you would need some high resolution sea surface temperature for sure. And I mean, I'm just looking at St. Helena Bay. Walker Bay is even smaller, and the blooms are very specific, and it's a different type of bloom. Some of it is toxic rather than deoxygenating the water and having that kind of effect. So being able to track that would also be useful. So if you could have an early enough kind of warning, you would increase the sampling earlier so that you know what's in the water.
Could you be specific about what resolution would be relevant?
Oh, so at the moment, I think I would probably be guessing a little, but the resolutions that we have been talking about, sub 100 meter with Krishna coming up LSTM, and then also even the 250 meter that Misaka was talking about last week. I think that will also be quite useful already because it's 4 times higher. You know, and what you really want to be able to resolve is the gradients, because there are other applications downstream as well with respect to fishing and the presence of pelagics at these fronts and how that filters down the food chain for other applications.
Okay.
It's still Danny.
We've got time for one more.
Hi, Daniele Ciani from CNR Ismar. Maybe just a very little follow-up comment. One thing we should probably keep in mind is also our capability in terms of temporal resolution for this very high resolution coastal processes. So we have been speaking about spatial resolution, but I guess we should think about the current and even near future possibilities of characterizing these processes, considering probably not sufficient constellation of very high resolution mission. So
Yes.
because I guess we are speaking about very high frequency processes and the observation capabilities we have with few satellites might not be sufficient. So keep that in mind as well. I don't know if there are any other comments about this.
No, I
Thank
think
you.
that's a very valid point. We should really aim to have a consistent constellation of high-res, ultra-high, near the coast, sea surface temperature satellites. Yeah. And take a leap into some machine learning to try and assist with the gaps that we experience.
Any more questions? Okay, chairman's privilege. I'm going to ask one last question, and that is, I was being. So, do you have any in situ validation data in these regions, in this particular region?
Yes, for the sea surface temperature and for the chlorophyll A concentration. Yes, I do. I just showed an example of one because I was looking at the place where it was the highest variability, and the L4 was the least effective. But yes, we have in situ data all along the coast that I can compare to the product. Some of it is a bit too close inshore. It's in the surf zone, so there's complete mismatch. But there's some nice regular lines that are being done in St. Helena Bay to monitor every month or so, and from this I can get some data as well. And I think we did a ISAR campaign also in St. Helena Bay.
Okay, I mean, if there was consistent, regular validation data there, one thing that we tend to do is when we do cloud masking, we see what's passed the cloud masking, but we don't get to see very often what has failed the cloud masking that ought to have passed.
Yes.
And so one of the big problems is that we screen data out, especially in strong upwelling regions.
Yes.
And you never get to see it. It never gets into OSTIA. It's not OSTIA's fault or MU's fault.
Oh, no,
necessarily.
no.
Essentially, the data are being masked out, and they may be good data. But you can use the did I get a good retrieval? Diagnostic to maybe give you a chance to adjust the cloud mask, customize it in those areas, actually adjust the cloud tests themselves, rather than having to do the filtering. You can't filter on something that never got in the first place. So, okay, I think we are now at the time where we can actually switch to Jorge's presentation. We've had 15 minutes of discussion, very good discussion, when Boris would have been talking about water vapor halos, which is something that I would have been very interested in. But are you ready to give your talk, Jorge?
Yes, that's fine.
Great, okay.
Should I go ahead and share my screen then? Okay.
Okay, so I'll quickly say Jorge is application of Coral Reef Watch and the multi-scale high-resolution sea surface temperature products to marine heat waves in coastal Hawaii. Take it away, Jorge.
Thank you so much. And I also just want to take the opportunity to say I so wish that I was there with everyone, especially with these amazing discussions. And but thank you for this opportunity. And the talk I want to give today is, and I think it actually follows up with Christo's talk on the application of data sets to the upwelling region off of Benguela. But I want to talk about the application of Coral Reef Watch SST and the multi-scale high-resolution sea surface temperature product to marine heat waves in coastal Hawaii. And one of the things I want to say off the bat is I don't want to give these kind of talks thinking, okay, this is then how we can apply everything, all of these data sets to every issue of marine heat waves. No, these are specific applications, which I think is something we always need to be aware of to this region. to this particular region. So just because, certain products are useful for applications and research in one region does not necessarily mean they'll perform the same in some other region. And I think that also is probably true for issues of upwelling. But I think there's some very, optimistic results from this comparison work for the coastal marine heat waves off of Hawaii. So the methodology, the marine waves were derived based on the 90th percentile for coral reef, using the coral reef watch sea surface temperature and the mirror SST data sets. Analysis was for the past basically 20 years. So I think it's approximately 20 years. So again, there's a slight difference here in the convention that I think climatologies for calculating the 90th percentile, they recommend based on 30 years, but I just wanted to say that up front also. And the results for the different, heat wave show, I think, good comparisons between OSTIA and mirror, but it also shows, at least off Hawaii, it shows some very important issues with respect to resolution, which I think is something as we approach these issues of high resolution and future data sets, we need to be very, very well, aware of, the importance of the high resolution. And I think this will be an example. So we looked specifically off of, also made comparisons specifically off of 4 stations, one off of Oahu, also Lanai, Waimea, and Paola. And, again, the results were, I think in good comparisons also with the in situ data. And I think one important point also is, again, as was mentioned in the previous talk, the CRW data includes OSTIA. So OSTIA includes geostationary data, which would give more, more cloud-free pixels. So to calculate the marine heat waves, the points were compared directly with the thresholds based on the 90th percentile. So just this is kind of as a motivating factor. We looked at gradients first. And by the way, I'm so sorry. I didn't even, my co-authors, this is work being done with Michelle Garrick and Gregory Halverson, also at NASA JPL, and both of them, and this is also important in terms, I think, for the future. Gregory's very involved also with EcoStress, as is David Weefy, and so this is just a motivating factor in terms of looking at the gradients off of that area. This is the gradients off of Hawaii, for one specific day. This is based on January 20th of 2003, based on the Coral Reef Watch, and also zooming in on the coastal area off of Oahu. So you can definitely see some important issues in terms of, yes, there are gradients, that you can identify, at least off of Oahu, that are very, very near the coast. So again, this is an example where gradients and resolution can be an important factor. And to show that this is the same time, January 20th of 2003, but for the mirror SST gradients. And you just see a huge difference in the gradients between mirror and Coral Reef Watch just for this particular day. And off of Oahu, you also see these, yes, very, very maximum gradient features off the coastal area of Oahu. So again, this is the motivating factor also for kind of comparing how all of this might translate into the derivation of marine heat waves. So just in terms of comparing the variability, of these gradients, the CRW, Coral Reef Watch had an average of 0.007 degrees Celsius per kilometer. Mirror was slightly higher at 0.024 degrees Celsius per kilometer in terms of the mean and also the RMS values. Mirror had a slightly higher RMS value, also 0.0, close to 0.04 degrees Celsius per kilometer. So again, the time series, we did comparisons with in situ data for locations, Pearl Harbor, Benguela, Lanai, and Waimea. And this is just, shows in the left hand, the left graphic shows the gradients based on, I'm sorry, not the gradients, I'm sorry, the SST based on the coral reef watch, and also the in situ data. The coral reef watch is in red, the in situ is in black, and you'll see definitely higher SST values as you go past 2015, to the present. And the same thing, very similar with the right is the SST values again for Mirror. This is off of Pearl Harbor and also the in situ data. And you see the same kind of general trend between Mirror and Coral Reef Watch. You see higher SST values past 2015. And, and just as a reminder, 2015 was when we had the intense warm blob in the Pacific. I don't think, in my opinion, things haven't been the same since then. And then this is off of the same graphs, but off of Pahuela. And you see again the similar trends in both the Coral Reef Watch data and the Mirror data. And then this is off of Lanai, and you'll see again similar trends. And you see even in the in situ data, you see much higher SST values also, which are consistent with the satellite data. So again, this is very encouraging. Both Mirror and the Coral Reef Watch indicate, the higher values past 2015 for SST, and that's consistent with the in situ data. And then this is for Waimea, same thing, and same kind of general trends. So now the next step, just to comment on the comparisons of the derived maximum SST values, because I think this is critical also from the different data sets. And one of the general trends is that in terms of the time of the maximum, it was around 2015, 2016, and it compares very well. Both the Mirror and Coral Reef Watch compare very well with the in situ data for the maximum values. And in general, the trend was that the in situ data was higher, had higher SST values than the satellite data, both the Coral Reef Watch and the Mirror. But in general, the trend, I thought this was a very, very encouraging result, that both satellite data and the in situ data compared very well to when you saw the maximum SST value during this period of time. And this just shows you summarizing kind of the number of marine heat waves that were calculated based on the methodology of the 90th percentile. And this is based on the Coral Reef Watch. And again, you see, some significant number of marine heat waves increasing to actually during this period of time up to 40. And you'll see especially off of Oahu. So there's definitely impacts in coastal regions from these marine heat waves. And again, zooming in on Oahu, you also see the marine heat waves that get very, very close to the coast. And this is based on Mirror. So one of the things you see is definitely an increase in the number of marine heat waves. But I think this is also, an area of future work in terms of how all of this is related, to high resolution. And this is an area that I think, with missions like EcoStretch and Trishna is going to be an area of really, really importance, and the application of high resolution also will be to marine heat waves. And I mean, you see in here also, zooming in on the area of Oahu, the differences you see in the number of marine heat waves, even close to the coast. So this could have a definite impact on in terms of understanding impacts of biodiversity in coastal regions and the application of the satellite to monitor these kind of changes. So the 90th percentile, a number, just to look at that, and a number of days above the 90th percentile. This is just a graph shows for Pearl Harbor, and this is for Coral Reef Watch, and you'll see that the 90th percentile is in black, and the actual SST values are in red. And you'll definitely see that, and this is other, I think, another very encouraging result is that in terms of the degrees Celsius above the 90th percentile, when the maximum occurs, they're consistent between the, the Coral Reef Watch data and mirror. So I think this is, another very, very encouraging result. So this is off of Pearl Harbor. Did the same thing off of, this is for mirror. And again, you see similar, similar results when you see the maximum and also for the 90th percentile. And then this is off of Pauela. And you see again, the maximum that occurs in the SST values. And also there's about a plus 2.5 degree difference between the 90th percentile and which is significant, the 90th percentile and also the SST value. And by the way, I'll just mention there was a very interesting paper written recently applying eco stress to marine heat waves in the Red Sea in certain areas, and they were getting similar results with the eco stress in terms of the degrees Celsius above the 90th percentile. But they also showed in that paper, again, the importance of high resolution in terms of doing these, what they call eco maps for that area. So again, that's a very interesting paper and the application of eco stress and the high resolution to this issue. This is the same thing for Pauela, and you see similar results. And this is for Lanai. And this is for, again, for Lanai, for Muir. And these results are all pretty consistent. And Waimea. And again, Waimea for Muir and the previous one was Coral Reef Watch. So the number of consecutive days above the 90th percentile, and this just shows you the increase, in the number of days above the 90th percentile, especially past 2015. And you'll see it almost, there are time periods. I just thought this was amazing. 150 days above the 90th consecutive days above the 90th percentile as you get to 2020. And again, this is for Pearl Harbor and Coral Reef Watch. Muir is in black and Coral Reef Watch is in red. And then this was for Pauela. And you'll see again the dramatic, the dramatic changes that happened past 2015. And again, this is Coral Reef Watch and Muir is in black. And then this is for Lanai. This is for Waimea. And I think the trend here is, again, you'll see how the increase in the number of days above the 90th percentile. And that's amazing to me. Over 150, or close to 150 days as we approach 2020 above that 90th percentile. And then this is just kind of a comparison again of the mean differences between Coral Reef Watch and Mirror at those 4 different locations. And I think the results are, overall encouraging. The correlations were all around 0.97. Mirror in general had a little bit of a higher mean value as well as mean square, but they were very, very close. So I think the comparison, at least in terms of between Coral Reef Watch and Mirror in this area, I think is very, very encouraging. So in conclusion, the results indicate that the higher spatial resolution, of SST data sets could be critical for resolving marine heat waves in coastal regions. And certainly, Hawaii is one example. And both Coral Reef Watch and Mirror are consistent in showing increases in marine heat waves based on the 90th percentile, especially past 2015. And the increases are dramatic. And, when compared with this in situ data, they are consistent in determining the maximum of SST, when the maximum of SST values occurred, and in general the degrees Celsius above the 90th percentile. Overall, I think the results are encouraging for application of satellite-derived high-resolution SST products, and also for monitoring of marine heat waves in coastal regions. But it also shows the importance of resolution in future missions like Trishna and applications of eco-stress. Thank you so much. Wish I was there with you. Thank you.
So we have time for a few questions.
Hello, George. I think these results are very important, and I agree with you that we need to evaluate also the impact of the resolution, because this, especially when I was discussing yesterday, proposing to have an effort on marine heat wave activity, we know that also in the future, when we have a high resolution satellite, before to build up a climatology, we have waited a lot of time. So the importance of the impact or resolution in the detection and is a crucial part to be considered. And I think we could simulate this part to understand how much changes the threshold and the impact in terms of duration and area covered by a marine heat wave. So this is only a comment, but I think it was not clear to me what type of climatology you use in these plots, but I'm sure that that the outcome that you show is a crucial part to consider.
Yes, and that's a great question. And thank you for reminding me. I didn't mention that, but to be consistent, I use the climatology. I recalculated the climatology from Coral Reef Watch to match up with the climatology of Mirror, which is over that 23 and since 23-year time period. And I did that just to, just to make sure about the consistency of the results.
Obviously, the presence of gradients at peaks and high resolutions impact also the climatology. So
absolutely, absolutely.
But
yeah.
Because the only things that we could do, because we have not high resolution satellite measuring for a long time now.
And it's interesting. One thing I wanted to check is because, in Christo's paper in terms of the impact of clouds, but I don't know much about. I need to check on that. I don't know much about the issue of cloud cover off the Hawaiian Islands, so I should have checked on that.
Yeah.
Because that could be also one reason why the results from the level 4 data sets are a bit better here. I don't know. That's also a subject, I think, of future work and also motivated by Christo's work on.
Yeah. I completely agree with you.
The questions?
Hi, Jorge. It's Andrea Pisano. Nice presentation. I was a bit surprised on the big difference on the results you showed by using MURE and the other data set on the number of marine heat wave detected. A very huge increase. Despite the role of this, the spatial, to what extent the spatial resolution plays in the generation and duration of a marine heat wave is for sure to be furtherly investigated. Otherwise, this, I was thinking on a difference in the SST provided by the two data sets used.
Yeah, I mean, that's a great point, and an interesting in that paper that they used EcoStress. I can't remember now what other, I'm sorry, what other SST data set they compared it with. But it was clear that, you know, the resolution was giving, it was consistent with, was also having an impact on the number of marine heat waves calculated in at specific points. So I think, yeah, again, this is an area of work for the future, and I think it's exciting. This is another, I think, I know it's been mentioned, but just to reiterate, you know, a motivating factor for issues like Trishna. And I think it's huge because this is going to have, I think, a huge impact on coastal applications, and also from what, you know, Christo showed, and the impacts to upwelling and also marine heat waves. This is a huge motivating factor, I think, for these future missions in high resolution. And I think one thing that I'll also say is that because we have a poster up with David Weesey and Danielle on application of gradients off of California. One thing I think it's important is to understand that all of these regions are going to be different in terms of some of the spatial and temporal scales. You know, for example, you know, the spatial scales of, you know, off of California for upwelling, and because of the California current system, go much further off the coast. And I think that's another issue, you know, and all of these for the future is comparison of these kind of problems also with currents and ocean currents. And I think this is where also, I'm sorry, I'm ranting, but this is also where I think incorporating things like SWOT in the future with these kind of SST products is going to be also very, very exciting.
Oh, another question from Chris.
Hello, Jorge. It's Chris Merchant here. So I don't know these islands that you've been showing us, Jorge, unfortunately. Never been there. But I guess they don't have much in the way of a shelf around them. But what is the tidal situation? Is there any impact of tides that are subdaily, obviously, when you're looking at your analysis?
I haven't seen any, Chris, but that's, I think, a question also for the future, right? And I think, you know, and maybe it's me. I haven't found a lot of previous work done for this area of Hawaii. So I think a lot of this is kind of going into a new into a new area. But yes, as far as I know, you know, I don't know much about the tidal magnitudes off of these islands, but I think that's an area also we need to check for the future.
William?
Jorge, this is William Skirving, formerly of Coral Reef Watch. I can comment a little bit about that. Basically, this comparison was a sideways comparison with your in situ data. The satellite data would have been sitting on top of one another. So you can't read a hell of a lot into the comparison of absolute temperatures from the in situ data with the satellite data. It would be worthwhile for you to look at doing that in anomaly space. With Coral Reef Watch, what we find is that almost all of the pixels are not over coral reefs because we can't get that close to the coast. And all the coral reefs are pretty much in the bays.
Yeah, exactly.
And the other point to make is the oceanography. The shelves, there is no shelf, so it drops off rapidly on all of those islands.
Yeah.
So you're over very deep water, and what you're doing is crossing your fingers that the anomalies, which will be derived from completely different absolute temperatures offshore, mimic the anomalies that the coral reef the corals are experiencing. And in general, in Hawaii, surprisingly so, that's exactly what happens. So the Coral Reef Watch product works around Hawaii largely through fluke.
Okay, no, thank you. Thank you for that point. Yeah.
Are there any more questions? I was just going to say that I was gratified that actually the Coral Reef Watch anomalies look rather similar to MUO, given the massive difference in spatial resolution. But I think probably
Exactly.
it's because it's sitting in the middle of the Pacific Ocean with, as William points out, it's a very, it's basically the deep ocean around the chain. So
Right.
actually anomalies do work quite well. It's not a massively, massive gradient area in comparison. A few through flows and things, but nothing nowhere near as severe as things like what Christo was showing. So
Yes.
we are actually at coffee break time already. So
Sorry.
unless anyone has any more questions, just thank the speakers we had this morning. And we'll resume the session after coffee break. Thanks.
It's on. Now it's on. Song. Okay. You ready? All right.
Okay. Thank you for Erica for dropping that beat. So if you could return to your seats, we can resume the session. Just giving that extra minute for people to get back. Some would say it's partiality because I'm a co-author on the next presentation.
Oh.
It's my favorite postdoc. Seonju Lee, she is my only postdoc. She's very good. Okay, Seonju Lee is going to talk to us about aerosol-induced biases in satellite sea surface temperature and a physics-based machine learning bias correction. Take it away.
Yeah, hi everyone. My name is Seonju Lee from University of Maryland, and I'm going to talk about our recent research about satellite SST bias correction using physics-based machine learning. Some specific atmospheric and surface conditions can cause the satellite SST bias. Additionally, the SST retrieval coefficients are derived under the assumption of a linear relationship, but real-world conditions often involve significant nonlinearity. So we apply the machine learning method for capturing nonlinear relationship and unraveling complex dependencies in SST regression coefficient. Last year's Chris meeting, I shared a poster on that topic. In that study, we used the environmental variable for as input variable to machine learning bias correction. We enhanced this approach by including CRTM derived output for providing more physics-based information. This is the workflow of this study. Firstly, we conduct the CRTM simulation under clear sky for simulating idealized condition and under aerosol sky for representing more realistic condition. And then we compare the observed this figure showed the method A SST bias for 2007 to 2018 daytime and nighttime. In this study, we focusing on reducing this method A bias. And so we compared the observed method A brightness temperature and simulated CRTM simulated brightness temperature. After comparison, we trained the machine learning model using this CRTM information, and we can obtain the reduced method A SST bias. And this is the data and method used in this study. We used the Expo method A level 2 data for 2007 to 2018. We selected this satellite because it maintained a consistent equator crossing time orbit through active orbit control for minimizing error issues. So it is very stable. And next is the matchup process. To assess the SST bias, we matched IQUAS-V data with satellite MERA2 and ERA5 with this observation time interval threshold and this distance threshold. And 11 by 11 pixels are extracted centered on matched pixel, and the distance-weighted average is calculated. And also we use the variety temperature observation for 2016 because it is only full year available in NOAA class. And we ran the CRTM simulation using version 2.3 CRTM. And this figure showed the comparison between observed Metal Bay bursting temperature and CRTM simulated bursting temperature. Theoretically, CRTM bursting temperature should match the observation bursting temperature. However, in some pixels, the CRTM bursting temperature is higher than observation due to residual cloud contamination. This effect is larger at nighttime than daytime because the cloud detection is less effective at night, leading to increased errors. On the other hand, in some pixels, CRTM brightness temperature is lower than observation caused by overestimated aerosol or water vapor in ERA5 and MERA2 used as CRTM input. But still, most points closely followed the 1-to-1 line. It demonstrated overall consistency. And CRTM can provide the brightness temperature and Jacobian information. The Jacobian means the sensitivity of brightness temperature to change in atmospheric or surface variables such as the surface temperature, aerosol, and water vapor. And also we can derive the SST using CRTM simulated brightness temperature. This equation is the ex-post Metal Bay cell SST retrieval algorithm. As mentioned earlier, the SST retrieval algorithm have some errors due to the assumption of linear relationship. So to evaluate the error of the SST retrieval algorithm, SST is retrieved using CRTM simulated brightness temperature and ERA5 SST. Here we using the ERA5 SST as reference because buoy measurements are not generally available for global condition. Provided the algorithm functions correctly, the input SST mean ERA5 SST and the SST derived from the retrieved coefficient should exhibit close agreement. And a comparison between the retrieved CRTM SST and ERA5 SST does enable the quantification of the algorithm's retrieval bias. And this figure shows the scatter plot of the ERA5 and CRTM SST. And this y-axis represents the difference between CRTM SST minus ERA5 SST. Although SST algorithm was constructed using ERA5 SST, but this CRTM SST does not equal ERA5 SST. This discrepancy highlights the limitation of the linear regression model, which is tuned to average environmental condition and does not consider the aerosol and water vapor effect. And the y-axis represents the CRTM SST minus brightness temperature simulated brightness temperature at 11 micrometer band. When the value of x-axis increased, the value of y-axis become variable, especially during daytime, because linear regression cannot fully capture the complex atmospheric effect. So we use this difference information as input variable to machine learning method. It has correct errors inherent in SST retrieval algorithm. And now we are ready for machine learning. And first we split the data into training set and test set, and we perform the tenfold cross validation on the training set for assessing model ability without wasting training data, without wasting training data set. And the input data is summarized here. These variables are considered to affect the satellite SST bias. The variables above this red dashed line are used in our previous study, such as satellite genesis angle, satellite view genesis angle, and difference of SST and 2-meter temperature, surface wind speed, and total color water vapor, and aerosol, and spatial temporal information. And now we added this CRTM variable for our new machine learning method, such as CRTM SST and delta SST and delta breath temperature and SST Jacobian, total color water Jacobian, and aerosol Jacobian for each band. These green variables are used only in nighttime bias correction. And our target data is the SST bias between method A SST minus V SST. We using this training data set and this library data, machine learning model run the expected SST bias under specific condition. Then we can subtract this expected SST bias from original method A SST. Then we can get the bias corrected SST. This figure showed our previous result during daytime. We compared the performance of linear regression, linear methods such as SSES, EOT, and multilinear regression, and nonlinear methods such as random forest, light gradient boosting machine, and deep neural network, and TopNet. Okay, I'm hurry up. So, also this linear method linear method provides bias improvement, but nonlinear model, especially LGBM, proposed more effective result. So LGBM is one of the tree-based machine learning, but the difference between random forest and LGBM is the random forest build the tree horizontally, but LGBM is build the tree vertically for optimization. Sorry. So here we select the LGBM as the best performing model because it shows the improved SST bias for global spatial temporal pattern with cost-effective computing time. This value shows the global bias and RMSE with method A and LGBM without CRTM, our previous result, and LGBM with CRTM information. This is our new result. So in nighttime, the RMSE is slightly improved here, but during daytime, the RMSE is significantly improved in LGBM result with the CRTM. The inclusion of CRTM-derived variables in the LGBM model significantly improved RMSE, suggesting that the physics-based approach better captured variability and reduced large prediction errors. This figure showed the spatial pattern of the bias improvement. Left figure showed the daytime and right figure showed the nighttime. And middle one is the LGBM result without CRTM information, and bottom one is the LGBM with CRTM information. You can see this, the remaining bias in LGBM without CRTM can clearly reduce in LGBM with CRTM information. And this figure shows the special pattern of the RMSE improvement. And since we subtracted the model result from method A original RMSE, so the blue areas indicate the region when RMSE is reduced. So the bluer means the better result. So in LGBM without the CRTM information, they focus, the improvement is focused on low latitude, but in LGBM with CRTM information, the bias improvement in middle latitude, even high latitude as well. And this is summary. So this study attempted to capture the bias pattern and eliminated the SST bias, like resulting from complex combinations of multiple variables using machine learning algorithms, especially to improve SST retrieval accuracy. We proposed a peaks-based machine learning framework that incorporated key output from the CRTM, such as bright temperature, aerosol, bright temperature, and Jacobian and SST retrieval errors. The LGBM model, especially adding the CRTM information, enhanced the SST bias correction by leveraging physically informed features and lead to more reliable satellite SST products. To our further study, we plan to use the 11 by 11 special 11 by 11 matchup grid to reduce this remaining local bias after machine learning method. Thank you for your attention.
I think we'll hold questions as I guess Blake's online. Are you online?
I am. Can you hear me?
I can. We can.
Excellent. Share. Okay. All right. Hi, everybody. My name is Blake Spady. I'm from NOAA Coral Reef Watch, and I'm presenting today a project led by Momo Yoshida, and we'll be talking about improving the understanding of uncertainties in satellite SST. So, as you would all know, satellite SST.
Sorry, Blake.
Yes.
You're not in presenter mode. I don't know if you're sharing the right screen right now, in case you wanted to.
Or was I see. Was it sharing like the?
Yeah, we see the whole like back end.
Okay.
Yeah.
Let's see if I can. I think you can swap that. Does that help? No.
No, but I mean.
Okay. Maybe. What if I do that? Is that better? No. Okay. Hold on. Sorry.
But if it doesn't work, then yeah.
What about? No, that's not working. I can see that doesn't work. Let me unshare and try something else here. Share entire screen. So that I think will be better.
Yeah, that's better.
Okay. Carry on.
Okay. So. Yep. So satellite SST, as you would all know, inform various climate, oceanic, and weather systems or processes. But what we use satellite SST for at Coral Reef Watch is monitoring biological responses. Now, these can be very fine scale when you're using satellite SST, fine scale responses such as metabolic or gene level responses all the way out to community or ecosystem level responses. And as individuals within a species or even within a population are highly varied, this using satellite SST to monitor these populations can introduce some really tricky problems and challenges there. So, and with myself, what we're looking at is obviously corals and coral bleaching. So we're not only looking at various individuals within a species, but we're looking at several individuals within several species on a reef. So this can be even more problematic. So very, very briefly, coral bleaching. I'll give an overview here. Corals are animals. They have a symbiotic relationship with a microscopic algae that live within their tissue. And via photosynthetic activity, this algae can provide up to 90% of that coral's energy supply. And when corals become stressed, it can break down that relationship, causing the coral to expel that algae from its tissues in a process called bleaching. And this can be caused by any number of stressors. But when we talk about mass bleaching, which is happening at very large geographic scales, this has only been linked to temperature stress. And if that temperature stress sticks around for a prolonged period, the coral can essentially starve to death. So when we're talking about temperature stress from a coral's perspective, this is defined as 1 degree above the climatological summertime maximum temperature. And that level of stress is called the hot spot. So this is the degree of our SST beyond the climatology. And the severity of bleaching is going to be related to the duration and the intensity of that hot spot. Now, at NOAA Coral Reef Watch, we produce a number of metrics and products that are almost all based on or derived from our daily global 5-kilometer satellite sea surface temperature product. And some of the relevant products that we produce for today's talk are, again, the hot spot, which is that instantaneous heat stress, the degree heating week, or DHW as it's often called, which is an accumulation of heat stress over a 12-week running window, and our bleaching alert levels. Now, the bleaching alert levels are basically a categorization of various DHW ranges, and at each one of these ranges or alert levels, we provide users with an expected reef-wide response to that level of accumulated heat stress. And as I mentioned earlier, the biological process here is quite tricky, and it's kind of filled with uncertainties. And when we're looking at these alert levels, we're using these somewhat broad ranges to define specific responses, and they have various thresholds. So we have kind of a full system of uncertainties here. And in 2022, myself, along with William Skirving and led by Jonathan Mittez, and I know both of you guys are there, so hello, we put together this poster, which we titled A Metrological Approach to a Coral Reef Bleaching Alert System. And what we tried to do here was to identify sources of uncertainty within this system. So we're looking at what's driving that uncertainty, and the focus was this uncertainty tree, which was in the middle of that poster there. And we're not trying to quantify errors. We're trying to use this as a tool to identify sources of uncertainty, to break down complex systems of uncertainty, and to clarify those relationships. And you'll notice within this tree, there are a number of text in which the fonts are various colors. And those are where we've identified potential sources of uncertainty within this whole scheme. And so the dark blue ones are ones that are well known or quantified uncertainties. The light blue ones are uncertainties that we don't have a full grasp on, but they're likely quantifiable. And the orange ones are uncertainties that are really unknowns, and in a practical sense are pretty much not quantifiable here. So this tree is divided into two halves, the top half and the bottom half, and it comes together at that green box there, which is our bleaching alert system. So if we focus on the bottom half of that tree and zoom in there, this is all the biological process and various biological aspects of the coral bleaching biological process there, sorry. And so what you'll notice there's lots of orange text here. So there are a lot of uncertainties in the biological process that are kind of just unknowables. We can't practically quantify these uncertainties. However, if we look at the northern half of this tree, we're now looking at essentially the DHW algorithm. And while there's not necessarily less uncertainty here, the uncertainties that are here, you'll notice, are far fewer orange text here. So these are uncertainties that we have a better handle on. We have a better ability to start to investigate these. And if you stared at this quite a bit longer, you might notice that most, if not, most of these uncertainties here are kind of SST specific. So that's when Momo Yoshida, again, the lead author here, the lead investigator, wanted to kind of take a step deeper here and investigate the uncertainties within the SST itself, specifically in the geopolar blended near real-time product. So we have a kind of beginning workings of an uncertainty tree here. A lot of work to do to tease this apart, but right away, Momo identified a few sources of uncertainty that are quantifiable that we could kind of sink our teeth into. And so those will be the grid counts at level 3, as well as correlation distance and SST variabilities. So if we're just focusing on the grid counts first there, we want to just see what the influence of data density is on the geopolar blended near real-time product. So we obviously have a blended product here with polar orbiting satellites, and we have a record of how much data is feeding into our 5-kilometer pixel for each data point or for each day in pixel there. And we can do the same thing with our geostationary satellite, see how much data is feeding into the pixel. And then we can start to understand what this data density, because this is quantified, what this data density is doing to the reliability of our values. So first, just looking at the satellite SST pixel compared to in-water temperature loggers, we can see that there's a fairly strong correlation here. It's not amazingly strong. It's not the best in the world, but this is just one small example, and it's pretty typical of what we might see kind of with any random point in time there. And so what we want to do is look at these grid counts. We have in the red circles our geostationary grid count total, and in those pink triangles we have our polar orbiting grid counts. And we want to see if periods like this, where we have fairly high grid counts, if those SSTs are performing better compared to something like this the next day, where we have a very low, in fact, 0 grid count for this day. And perhaps more importantly, what we want to understand if this pixel, again, that has 0 grid count after a fairly high grid count the day prior, is performing significantly better than this one that has had 3 days of 0 grid counts again. And so what we might expect here is to see in these red dots, we have our sum total grid count among all satellites, and we see a very high one for that example there. And we want to see if the absolute temperature difference between the satellite and the in-water logger is, in this case, very low. And here we might expect, if the grid count is 0, that it would be very high. However, when we looked at this among 12 sites within the Great Barrier Reef off of Australia for some limited data periods so far, you guys might not be necessarily surprised, but maybe pleased to see that there was absolutely no correlation in any of these at all. And that will be for probably a million reasons, some of which I heard William mention, 10 or 20 minutes ago. But this is just a limited data set at this point, so we're going to look into this more regardless. But with that in mind, we still want to see if we can, instead of looking at the real data, thin this data, kind of have a simulation and inject an error into these pixels and see if we can basically semi-randomly remove data from our process here, and then rather reprocess the data, and then see at what point this is having an effect and what kind of effect that is having. And so by injecting an error into a simulated error into our process, we can have a better understanding of what that error might be, because we have some control over how that error comes about. So, we can do this with our grid count as well as correlation distance, SST variability, and possibly other sources. If anybody has any leads of good approaches here, we'd be happy to hear them. And then we can validate that data. And the goal here is to come up with a reliability metric. So by coming up with this reliability metric, we hope to inform users of the uncertainty around our values. Now, I think a lot of people can use this in a lot of different ways. Myself, the way that we at Coral Reef Watch would want to use this would be to use this in our heat stress metrics, of course. So as I said earlier, there's a lot of uncertainty around the biological process of coral bleaching. And at Coral Reef Watch, there's not a lot we can do to help the user from that biological point of view, but we can provide them with information about the uncertainty around our accumulated satellite-based heat stress measurement. So again, corals start to become stressed when that SST is warmer than the climatology, and we only begin accumulating those into our degree heating week, which is our metric for predicting bleaching, when those SSTs are at the MMM+1. So when we have here 12 weeks of daily SST, and we have that dotted line going across the graph there, that's our threshold for accumulation into the DHW product. Only those days in which that SST is above that line are going to be accumulated into the product. All of those other pixels, some of which are pretty much right on that line, just slightly below it, are ignored by the algorithm. But are those heat stress or temperatures, rather, ignored by the coral itself? In many cases, likely not. So we want to provide a distribution of uncertainty around our values of SST, which is kind of a function of our grid count, our prior day grid count, our correlation distance, and potentially more. And after doing that, we can get a kind of uncertainty or an error around each SST value. And then when we begin to look at our DHW accumulations again, we can see that now perhaps several of these, which were formerly below that line, might now be above that line. And if we recalculate our DHW with that in mind, it could be as high as 8 degree heating weeks, while it was formerly 6 degree heating weeks. And on the inverse, we could look at those that are now crossing under that line, and we take them out of the accumulation, and that DHW goes from, again, 6 down to just 4 degree heating weeks. So this all feeds back into our alert levels. Because these alert levels give users a specific expectation, or more kind of a general expectation, rather, at each DHW range. Again, that last DHW example was at a level of 6 degree heating weeks. And that gives the users an expectation of a reef-wide bleaching event. Well, if we add that uncertainty that leads the DHW to potentially be as high as 8, well, then those managers might expect a mortality, a significant mortality event. So we hope to provide the users with this SST reliability metric, which can then feed into our DHW metric as a reliability metric for that, and then give the users a more informed tool, a better tool for informed manager decisions. So I'll just like to thank everybody, especially Momo, who has been leading this, and I'll be happy to hear any feedback or take any questions.
Thanks, Blake. I'll let you run on a little bit because think we wanted to see that last little bit. William, you have a question? Or comments then?
More a comment than a question. So, Blake, first of all, I really like the logic behind the project. It's good, but you've chosen, especially from your perspective, given that you are interested in coral reefs. 85% of all coral reefs in the world live within 5 kilometers of a coast, and you chose your test pixels when you did the initial look all offshore. They're perfect. They're best case scenarios. I would like to see the same analysis done with a pixel hard up against the coast, so that you have less information around the pixel to feed into it with the blended process. So that would be a harder ask to get right. And indeed, it's the one that Coral Reef Watch wants to get right. So that's my suggestion.
Yeah, great. I think that's a really excellent point, William. I appreciate that. So I will pass that along to, I think some of the authors are listening there, but I'll make a note of that, and we'll definitely look into that. Appreciate it.
Other questions? Yep. John?
John Mithouse, University of Reading. More a comment, really, in that the initial poster was about metrology, the measurement, how metrology is applied to provide uncertainties. And you should be aware that a metrological approach isn't quite the way you're approaching it. From a metrological, from my point of view, some of the statistics you're doing are taking my signal and comparing against another signal and inferring what the uncertainty should be. The metrological approach, you do it bottom up and you try to work out at each step all of the different processes that go into constructing the uncertainty, try to work theirs out. So there is somewhat of a disconnect between the original post doing. That's not saying, of course, that doing it the way you're doing it, you won't gain added information. But metrology, it's not the way that we would try.
Gotcha. Yeah, you broke up a little bit there, but I got most of it. Yes, so I think that kind of these two ideas kind of merged. So, you know, Momo was already down this path for this thesis, and I showed her this poster, and they kind of came together. So I think the idea with the uncertainty tree was to really just to identify some of those sources. I don't know that Momo necessarily thinks that her approach is a metrological one, although I think we would be interested to discuss more for some potential metrological approaches we can work into this. So yeah, I appreciate that.
Like I say, it's a comment.
Yeah.
Do we have other questions? I'm just going to briefly make a comment, and that is that the fact that there is sort of no correlation observed between the grid count and the actual location and the analysis, this is not particularly a surprise for me, but it's definitely an understanding thing that bubbles up every now and then. How many pixels are actually contributing? And the answer is many, many, many pixels, because the minimum radius is 8 grid cells in all directions. So that's a lot of data that's not actually sitting on the thing that's still contributing to the anomaly estimate. And that's just something that, you know, people who use level 4 products, they love them because they're global and gap-free and gridded, but they still can't get away from the fact that this gap-filling procedure uses surrounding information with correlation length scales. And it's just an important message to get across, I would say, that as you said, Blake, it is reassuring, certainly in these circumstances. But then again, William highlights the fact that there are other circumstances where, you know, maybe you're getting nothing and in that actual location ever, because essentially it's too close to shore and things are getting screened out. One other thing I should mention before we wander into the GRIS priorities area is don't forget that Seonju also gave a presentation. So if you've got some questions for her, you can ask them now as well. Anybody have anything? Did anyone have anything to ask about the bias correction presentation that Seonju gave? Got excited by the pictures of coral reefs, didn't you? Oh, hang on, here we go.
Just ask one simple question perhaps. Okay, I think there's also a simple like bias correction method, like using a statistical analysis. Then we get a quite simple bias for the whole